In this video, I'm going to talk about electric fields. Electric fields are a specific type of field, so let me talk about fields in physics in general for a minute. The idea of a field is in answer to the question or the problem of having action at a distance forces. In the first semester of physics, almost all of the forces that you encounter are contact forces. They happen because two objects are in contact with each other. For example, friction. You can only have friction when two objects touch each other. Almost all of the forces from intro physics, tension, friction, the normal force, air resistance even, which is a kind of friction between air and the object, spring forces, almost everything from intro physics, except gravity, is a contact force. Gravity is one of the four fundamental forces, and it is action at a distance. You know that gravity is the force that keeps the planets orbiting around the sun. Very much distance there. When an object falls and is not in contact with the Earth, it's the gravitational force of the Earth on the object that causes it to fall. So gravity is an example of an action at a distance force. So is the electric force. I've already made a video talking about Coulomb's law, which is the force between two charges separated by a distance. It's an inverse square law. It's 1 over the distance squared. And I will be writing that in just a minute. A field is we think of the field as extending everywhere through space due to just one object, in this case, just one charge. So if there is one charge somewhere in the universe, there is a field that extends everywhere throughout the universe. In the case of the electric field, it is a vector field. Here is an example. I am using the PhET simulation called Charges and Fields by the University of Colorado Boulder. I highly recommend it. The link is right there, and I will have it all in the description. You can play with this yourself, and it's really fun. So here's an example of, this is just a static picture, but if you go to the simulation, you'll be able to move things around, and I actually will show you that too. But let me just pause here for a second. So here's an example. Here's a picture of, in the center, the mouse cursor is kind of over it. There is the red positive charge in the middle of this picture. Then off to the side, there are controls from the simulation. So I just screenshotted the whole simulation here. There's a positive charge in the middle, and the arrows show the direction of the field. So the direction that the arrow points, in this case, all away from that point charge, and I'll talk about why that is in just a second. But what I wanted to emphasize here is, it's really hard to see in the video, but the faintness of the arrow represents the weakness. I said it the wrong way. The darkness of the arrow, the darker the arrow, in this case white, the brighter white the arrow is, the stronger the electric field is. So where the arrows are the brightest white, towards right in the center, near where the charge is, so this area right here, is the strongest electric field. And then as the arrows get fainter and fainter, that is indicating the electric field gets weaker and weaker. The field goes just like the force. It's also a 1 over r squared dependence. So it should get weaker as a factor of 1 over r squared. And indeed, that is what we will see happen. So this idea of the field extending everywhere in space solves the problem of the action at a distance, because any new charge that we put into this region will be directly in contact with the electric field that's already generated by this charge. Or if there's a configuration of other charges, whatever field they generate, as soon as I put a new particle in there, it will interact. So if I put another particle right here, it will interact with the field, and it's directly in contact with the field, because we imagine the field extending everywhere in space. So anywhere I put that charge, it's in contact with the field. Let me just show you, just because it's kind of fun, a little bit more about the simulation. Also, you can't sort of tell from this static picture what's happening in the simulation is there's an arrow, the middle of each of these arrows is in a grid on the simulation. And as I move the charge around, you can see that, that the arrows will move along with it. There we go. So I'm going to grab that red charge and drag it around. And you can do this yourself if you go to that link and play with it. So you can drag it around and you see. So you see it's activating. Some of the fainter arrows may not be easy to see, but you can see that it activates those as it gets farther and farther around. So I paused it in a slightly different spot so that you can see here the charge. You can see it more clearly because it's not on top of one of the arrows. So there you can see that again the on the cross pieces where it's sort of in a line, the arrows extend directly away from that charge. Actually, they're directly away in all directions. It's just kind of hard to tell for some of the ones that aren't straight. It'd be nice to talk about the direction of these charges, how I know they're opposite, and I'm going to show you a negative charge. And when I have a negative charge, it actually flips the direction. So there's a negative charge, and we can see that all the arrows are pointing in towards the center. Let me flip back to the positive charge there for just a second. In a sort of generic way that will turn out to work for both, I mentioned gravity, for both gravity and the field, we sometimes say that the field is defined as the force divided by the property that feels the force. In the case of gravity, the property that feels the force is the mass. And in the case of the electric field, the property that feels the force is the charge. So we're going to take the Coulomb force, plug it in here, and divide by one of the charges. And I'll show you how that works. So we had the field is the force over the property that feels the force. In the case of the electric force, we're going to use Coulomb's law, and we're going to use the letter E for the field. So the electric field is a vector, just like force is a vector. So E will be the placeholder for the field for the electric case. And the force is the Coulomb force, K big Q little q over r squared in the r hat direction divided by little q. I can just cancel a little q, and that means that the electric field vector is equal to K Q over r squared in the r hat direction. As long as this Q, the source charge, now there's only one charge in this picture, and we have the field spreading everywhere through space. In the case of one positive charge, this Q would be positive. R hat is, if we imagine that the red charge there is at the origin, R hat is the direction of the position vector extending out from the origin. Or if you like, it's the spherical coordinate R. Oh, this is a 3D picture, so I can only easily show you a 2D picture, but you should imagine that these arrows could extend everywhere. So these arrows are extending towards me and out towards you, with the same gradation being the farther away you get. So you can imagine just rotating that picture. Since it's a point charge, you could rotate it any direction you want around that red charge, and it should be symmetrically the same. Whereas if that Q is negative, then if Q is negative, then we get E equals negative KQ over, I have to put the absolute value sign, and negative R hat flips the direction. Where's my minus sign? There we go. So for the negative charge, notice the color difference is blue in the simulation. You can see at the bottom they're labeled. So for the negative charges, we expect them to point towards the center because the negative sign indicates that the direction of R hat is flipped. So negative R hat points towards the center. Negative R hat is centripetal, toward the center. And R hat is radial, radiating outward from the center of the circle. We could also use this, I had mentioned that it's a 1 over R squared. We can also use this to calculate numbers, and the simulation has the ability to do some numbers first. Oh, before I do that, I'm just going to show you a picture of a dipole, which is just 2 charges. So there's the negative charge again, and I'm going to grab a positive one from the bar down here. Okay, sorry. First I move the negative one around a little bit. I'm trying to center it. I don't know if you can see the grid lines, but I'm lining it up exactly on a grid, on an intersection of grid points there. Then I grab a red one and move it up. Now you can see the field generated by a dipole. So in this case, we would have to add 2 of these terms. I'm not going to do that right now, but it would be very easy to do. And you can see, I have a better picture where they're, instead of lined up on the intersection of grids, they're lined up with the arrows. You can see on the direct line between them, we can see that the arrows all point from the positive red to the negative blue. They all actually point from the red to the blue. It's just that some of them take longer to get there, and some of them in the center go right along the line. That's definitely a problem we could solve, but I want to show you, like I said, I want to show you that the simulation can do some numbers first. We'll start with just a, if I change the length, if I double the distance between them, what happens to the field? I can do that with the sensor arrow on the side. So there's a sensor over there, and if I select that, I can move it around and show you how the length changes. Oh, the arrow is a little bit hard to see. I hope you can see it. So I'm trying to line it up there. I'm trying to get it, when I get it straight, it wasn't quite straight. So you can see that there's a slight downward angle there. So I'm trying to line it up so it's straight. And it's 1 square away. If you can see the grid, it's 1 square away. I'm going to try to count. So I'm going to try to count grids for you. And if I have this all lined up correctly, when it's 1 square away, I don't want to erase that, but that's okay. I can rewrite it up here. For a point charge, we have that the electric field is equal to KQ over R squared R hat. That's the exact same equation I had written. I'm just rewriting it so it's up at the top. So if we choose a particular R, in this case it's only 1 square, but rather than say 1 square, I'll just call it R1. It does turn out there is a grid on the bottom, but I haven't turned it on yet. That will turn out to be 1/2 meter, I think, on the particular axis that they have. So if I have it 1 square away, and then I move it, and if you count, so the distance, so when I say 1 square, I mean the distance, the R, which is the distance between the charge, and the point where you're interested in. So I divided by little q to get I divided the Coulomb force by little q to get only one charge left. And this is the charge, the red, and this yellow is the sensor. You can think of it as being a very, very, very tiny charge that I'm putting there just to test. It's called a test charge, just to test what the force would be here. And then I can divide out that q to figure out what the field is right at that point. Then this red arrow, which if you could see the grid well enough, you can count, and it's about 8 squares. And I realize there's a unit problem here. Distance and force can't be squares, but for the sake of just checking if it makes sense, we'll say that works out okay. So the electric field strength is about 8 squares when the distance between the two charges is about 1 square. Now I'm going to move it so that the distance between them is about 2 squares. Oh, I'm still counting over there, counting my approximately 8 squares away. Okay, now I'm going to move it. And now, I don't know how well you can see it, but when I double the distance so that R2 is 2 squares, which is another way of saying 2 times R1, then it looks like the electric field strength at that point is about 2 squares. So another 2 squares. So the red arrow, so there's 2 squares between them, and then another 2 squares for the length of the red arrow. We would totally expect this, so E1 is equal to KQ over R1 squared, just doing the magnitude right now. And then E2 would be KQ over 2R1 squared. When we square that 2 in the denominator, we get KQ over 4R1 squared. So that makes sense. So it was 8 squares and it became 2 squares. And so we expect the original 8, so the KQ over R1 squared was equal to 8 squares. And we'd have 8 squares over 4 equals 2 squares. So at least in terms of the proportion, it is indeed exactly what we would expect. So they are in the simulation. I said you can actually get numbers, but in the simulation they are being very consistent, keeping the numbers the same. So we started with a separation distance of 1 square. And that had a strength where the electric field was 8 squares long. Then we doubled the distance, and because that is squared, that's like dividing by a fourth, or sorry, dividing by 4, which is like multiplying by a fourth. And our original number was 8 squares divided by 4, and we got 2 squares. All right, let's turn on the actual numbers and see what that looks like. Oh yeah, there, it's actually there. It's just really hard to see. Oops, did I lost it all the way back to the beginning? Let me put it back here and then hit pause so we can still see it. When it hits all the way to the end, it just goes to that play button. All right, so let's check. Oh, so there I was saying, so there you can see the arrow representing 1 meter. So we can check the numbers and see how this works out. So those are separated by, it's very hard to tell, but those are 2 squares separated, which means they're 1 meter separated. And again, if you can read down here, the magnitude of that charge is 1 nanocoulomb. So we can just plug in those numbers. K is 9 times 10 to the 9th Newton meter squared over Coulomb squared. Q is 1 nanocoulomb. Nano is times 10 to the minus 9th, and it's coulombs. And then the distance between them is 1 meter, and that will be squared. We get meters squared, cancels meter squared, and there's a coulomb there, and coulomb only cancels one of those coulombs. So it turns out that a unit of electric field is a Newton per coulomb. And so we go back here. Do you want color? No reason to flip colors. We go back there, and let's see. We have a 9 times 10 to the 9th and a times 10 to the minus 9th, so those will also cancel. You add exponents when you multiply, so 10 to the positive 9th times 10 to the negative 9th means you get 9 minus 9 is 0. So the powers of 10 go away. So this works out beautifully to be 9 newtons per coulomb. The direction, so the direction, that would be what I would call the regular old x hat direction. You might have, depending what book you're using or what class you're taking, somebody might use an I hat instead of that x hat. That simply, the hat means it's a unit vector, means it has length 1. So I can go ahead and repeat that down here as well. And indeed, that's very, very close. So what the simulation says it says it's 9.13 newtons per coulomb. Actually, I believe it says volts per meter, but that's the same. That's a different way to write it, but since you might not have seen volts yet, I'll stick with newtons per coulomb. So they got 9.13 and I got 9. It's very, very challenging to line up those dots. You should try it yourself. It's very challenging to get the charges and the sensors to be locked exactly onto a grid. That's a feature they should have. It should have snap to grid. I don't know if it does. I should have looked. So I highly recommend this simulation. I highly recommend that you play around with it. And again, the link is here, and I also will put it in the description of the video below.